the first point concerns the position aspect. Okay, fine, you ensure the ontological aspect of the outcome seamlessly by starting from the theory level. You introduce the ontology of the position as an additional postulate. And also one may say ensure the macroscopically distinct states, okay, I can ensure to a sufficient degree of accuracy. Of course, there is this conceptual point there. But this is a serious point that since at the wave function level, so to make the Bohmian resolution of the measurement problem entirely satisfactory, one needs to ensure all these three. And this part for the closed system means closed system plus apparatus, one cannot ensure. And that is where the role of decoherence model comes in. So, what decoherence model does?
One question. So usually, when one studies standard quantum textbook quantum mechanics, then one of the things which comes up is that you make a measurement and then you change the wave function. You just project it into the eigen state. So where is? I mean, I don't see that aspect.
No.
In anywhere.
Already I made a remark that what is unsatisfactory about that statement, that the wave function changes. That was Dirac's. That ignores the interaction. So if you describe quantum only the entire process quantum mechanically, then what I had indicated, you have to include the apparatus, interaction, and then you cannot make that state. So that's
so then it is simply.
So the collapse, even to introduce the collapse postulate, one has to do it carefully. I will come to the collapse model. So the Dirac version of collapse postulate is very crude.
So is a question that even if you're talking about the system and apparatus together, where would you, how in this model would you reproduce what is done in the lab, which is to put in a projection of the
because you have some entangled state of system and then some pointer value plus some other system value and some other pointer value. But then whatever standard quantum mechanics would then tell us that if you measure one pointer value and you immediately try and measure it, then you measure the same value again. So you don't see an entangled state after measurement. That was what he said it completely.
Because then it's a regression, means another measurement means you have to include another apparatus. But what I'm saying that point is a secondary problem in the standard model. You do not ensure even after the first measurement that definite outcome.
Yes.
Because you have a pure state. That was the whole point.
Well, I don't quite understand. I might have missed the crucial thing when I was out of the room, but the pointer variables have a definite position.
Yeah, pointer variables have.
Why is that?
No. In the theory we have the pure state. So the pointer variable this position or that position.
No, I mean in the Bohmian.
Oh, in the Bohmian it has a definite. He's not talking in terms of.
I thought you were talking about.
No, he's talking in terms of collapse first.
orthodox version.
I thought weren't you asking how the Bohmian model
accommodates
collapse?
The Bohmian model does not have
context of the Bohm model. No, but how does it get the practical effect of the collapse? That's the question.
That comes because of this. That comes because of the orthogonality of the apparatus states. When you try to follow the particle equation of motion after the first measurement, the entanglement, it is the only one part of that entanglement function that contributes to the further evolution. That psi which guides the motion of the particle.
Yes.
So in any one outcome, that is the apparatus position has been singled out.
Yes.
So it is a particular position that is important after a single run.
Equivalent to the collapse?
Collapse. That is operationally equivalent without bringing in collapse. Effectively. Because if you calculate that the apparatus position is in that part of the wave packet. Provided you ignore these points, the earlier points, the overlap between the two wave packets and the possibility of interference between these two wave packets. If you ignore those 2 points, then the subsequent. So that's why those 2 points I mentioned, that those 2 points are vital, that the wave packets are assumed to be non-overlapping. So that you don't get any contribution. That psi which is guiding the motion of the particle.
But if you have the interference between them,
because that size of that coordinate del S, del X, so the position of the particle is the derivative. So if the particle is in one wet packet or the other, so it is that part of the wet packet which guides its motion.
But what about situations where there's a symmetry, like a spherical symmetry or something? So that the outcome doesn't split into, well, something like a wave packets. You know, like the decay of the...
And the decay will be a problem, that a non-uniform.
That's equal zero.
Yeah.
State.
Those kind of situations, but then decay states, then decay products, one has to analyze it. People have to, in that decay, there are also other problems, like in decay products, when you make measurements on the decay product and identifying the decay state, which has been particularly important in particle physics, for example. So there have been some discussions about how to relate the measurements on the decay products with this state of the decaying particle at the time of decay. So
I think just one thing, one way of answering your question, I think, is that after the measurement is over, the apparatus variables have a particular position. What you can do in the wave function is a function of both the system variables and the apparatus variables. But the apparatus variables have a particular position. If you may not know it, but you'll know it approximately. That's related to this issue of overlaps. But if you knew it exactly, I mean, we can talk about it because it's in the theory. If you just condition on the values of those and let the system variables vary and think of the others as fixed, then you get a wave function purely for the system. And that's the collapsed wave function. In other words, you take the wave function as a function of varying position, varying system positions, holding fixed the positions of the apparatus as parameters. For each value of those parameters, you have a different wave function for the system, and that's the collapsed wave function. It corresponds to that outcome of the measurement.
So this happens dynamically then?
Yeah, they're dynamically. It's a dynamically moving, because provided you put in those assumptions that that position has that fundamental status and it is the non-overlapping thing, and also the possibility of interference between these two states. That is crucial.
So
the possibility of interference is there, then it will not be effectively seen as collapse.
So finally, the original Bohm model does not involve any dynamical description of collapse.
There is no explicit collapse invoked in that sense, but it effectively ensures what collapse does without having the ad hoc nature of collapse possibility. But that is replaced by those assumptions about the ontological reality and the position.
But those are not assumptions in the sense.
Yeah,
they're external assumptions.
Yeah.
They're just they're things which could be confirmed by calculation in principle.
Yeah.
And then it's just a question of just calculation comes out right.
Right.
Or comes out wrong.
Right. Yes. The consistent.
In the last small bit, in the context of the presence of non-classical correlation, say for example entanglement, Bell's proposed the local hidden variable model, wherein there was a decisive and a neat way of experimentally testing the presence of non-classical correlation through in the form of Bell's inequality. And the violation pointed out to the same, the presence of non-classical correlation. So in the context of this measurement problem, or in general, does the Bohm's model for quantum mechanics have any decisive experimental verification? But if it is not there, then I think
no. All these different approaches that I'll be discussing, they're arising from the fundamental conceptual need to address the measurement.
Yeah,
but then.
But does the Copenhagen interpretation have any
then there is the collapse,
experimental
and then there is the collapse model also,
Right,
that actual collapse has occurred.
tests.
So that exercise is going on. You see, the Bell's theorem, it took time, 1964, and then even to realize it. And also some aspects of measurement problem are now being tested through Leggett-Gark inequality.
no, but Bohm's was before Bell's.
Bohm's was an inspiration for Bell.
Yeah.
If Bohm didn't happen, Bell wouldn't have got. Because that question that came up to Bell's mind, that Bohm model is internally consistent with quantum mechanics. But there is a feature of non-locality present in Bohm model that one can work out. If you take an entangled state, EPR case, work out the trajectories. So this non-locality prompted Bell to wonder that is any hidden variable, any such description of quantum phenomena has to be necessarily non-local, or can non-localities in Bohmian model is removable or not? That was precisely Bell.
But there the motive was very clear.
No, the Bell, because in the context of Bohm model,
But
also one of the motivations underlying Bell's inequality was the notion of realism. So he needed to assume realism because he believed in measurement problem.
Well, I mean, the way I look at it, it's more or less like a probability theory versus probability theory.
I'm talking about how this, and the Bell's inequality involves the assumption of locality plus realism. Now, this whole, unless measurement problem was not there, the whole question of why one should consider an inequality derived from the notions of locality, realism, and its incompatibility with quantum mechanics be important, be a worthwhile exercise. Because realism was necessary for the measurement problem as a measurement outcome, and already Bohm model was an example that there can exist a realist description. So Bell asked what kind of general restrictions I can give on such possible reality. So people forget that this important heuristic purpose, it is not only heuristic, it's an understatement. In fact, the whole predictive success comes about not only in a direct way in the history of science. This is how all these exercises paved the way. In fact, that we like also in the same spirit as measure theory is also done, that immediately one cannot conceive of experiments directly, but they will lead to questions and formulate. And already the Leggett-Kirk inequality is an example. Why this? Because of measurement problem, those assumptions underlying Leggett-Kirk inequality were motivated, non-invasive measurability and realism. So they are testing that whether those assumptions that are systems which can function as apparatus are true or not described quantum mechanics. So as a spin-off of all this conceptual exercise, you get, that is what this entire subject has been telling. You can lead ultimately to experience. It takes time to pose and may not be directly experimentally tested, but have relevance. And I will I'll point out another pragmatic example. But before that, just a brief remark about the decoherence.
Sorry.
But
what is the answer?
But I think about the time problem is there. So
Yeah, no,
so
please
let me see
I
how.
believe that there is no T. Let me check.
no, but what is the final answer? Have people worked out some inequality or not?
I think it depends upon the time constraint. I can give I answer in 5 minutes or half an hour, depending
So
upon.
there is T outside. Now the question is, what is?
Now, so
everybody's,
what time?
Is there a time constraint in terms of? Okay, we could break and then come back in, and you could decide when is this a good time to break?
Yeah.
So then, before you start on the
Yes.
decoherence functional.
So what basically, let me just indicate what I yes, already. So what I'll briefly indicate. So you have I've already given you one example. So there are many such examples, but I'll just pick up on since the issue of collapse was brought up. So the explicit collapse model, just to indicate to you broadly the spirit of that model and what is the criticism of that model with respect to solving the measurement problem. So that are 2 or 3 slides, and decoherence 2 or 3 slides. But what I'm keen on ending this talk, and then one can go on discussing about various other approaches, but we can do before. And that is this biomolecular example of quantum measurement problem. That is very cute example that shows the difficulty that can occur in the understanding measurement problem at a laboratory real life level that answers operational point of view that why quantum measurement problem is interesting. Because biomolecules occupy a strategic position between micro-macros. So long people talk about transition from micro to macro, but this transition takes place through the mesoscopic range. And at the measuring apparatus need not necessarily be macroscopic in the sense of a counter or slit. A biomolecule can also act, and that I will give an example. That poses some interesting new, sharper questions about the measurement problem and shows that there are lot of things, and so new approaches are needed for understanding the complexity of understanding the machine.
So should we take a break
Yeah.
now and then come back in about 10 minutes?